Good day everyone. In this video we are going to show about automatic anesthesia control.
We will show the theoretical background of anesthesia and we will show how to solve the problem step by step.
Hi, I am Kabir Hossain. I am a student of University Malaysia Perlis. My course is Communication Engineering.
Hi, I am Munef Hasan Abdullah Nasser. I am a student of University Malaysia Perlis. My course is Communication Engineering.
Anesthesia.
If you are having surgery, your doctor will give you medicine called anesthetic. Anesthetic reduce or prevent pain. There are three types: local, regional, and general. Local numbs one small area of the body. You stay awake and alert. Regional blocks pain in an area of the body, such as an arm or leg. A common type in epidural anesthesia, which is often used during the childbirth. General makes you unconscious, you do not feel any pain, and you do not remember the procedural afterwards. You may also get a mild sedative to relax. You stay awake, but you may not remember the procedure afterwards. Sedation can be used with or without anesthesia. The type of anesthesia or sedation you get depends on many factors. They are include the procedure you are having and your current health.
Introduction of the project.
Anesthesia can be administered automatically by a control system to ensure adequate operating conditions for the surgeon. Muscle relaxant drugs, which block involuntary muscle movements, are administered. However, an anesthesiologist may sometimes fail to maintain a steady level of relaxation, resulting in a large drug consumption by the patient. By introducing the concept of automatic control, which results in a considerable reduction in the total relaxant drug consumed.
Aims of our project.
To reduce the amount of relaxant drugs consumed by the patients, to maintain a steady intake of drugs with regards to the suitability of each patient.
Objectives.
To calculate the gain and phase margin of the system. To design a compensator that has phase margin at least 50 degrees.
Methodology.
The transfer function of the system is calculated by cascading both of the Z of S functions. The project is then conducted by using Scilab software. The values from the transfer function is fed into the software to plot the Bode plot and acquire the gain and phase margin of the system. The new gain crossover is determined from the graph and alpha is calculated so that the tau and alpha tau can be found. Hence, the values is substituted in Scilab once again to confirm if the phase margin is at least 50 degrees. Here is the question that we are required to be solved that you can see on the screen. An automatic anesthesia control system model is shown in the figure. In this figure there is an input R of S and there is output Y of S, and here also have the controller, a person, and it also indicate this is a feedback control system. So the part A of the question is draw the Bode plot of the system, determine the gain and phase margin of the system. Assume k equal to 3. Part B of the question is you are required to design a compensator, lead or lag, so that the phase margin would be at least 50 degree. Produce your design. To solve the part A of the question, we need to find the transfer function of the system. As k equal to 3 is given, so we get the final transfer function. As you can see, the numerator of the final transfer function is 3 and the denominator is s times 0.3s plus 1 times 0.6s plus 1. After that, we will insert all of the values of the transfer function into Scilab to get to generate the Bode plot and determine the gain and phase margin of the system.
Now I will show how to use the Scilab to draw the Bode plot to get the phase margin and gain margin.
To draw the Bode plot and get the phase margin and gain margin, we need to write the code in Scilab software. After writing the code, we get the Bode plot that you can see on the screen. And from the Bode plot, we get the phase margin is equal to 14.537003 and gain margin is equal to 4.436975. From the Bode plot, phase margin is 14.54 degree, but we need at least 50 degree phase margin. Taking into account 5 degree safety margin, we need to design a 55 degree phase lag network. Now I'm going to show all the steps to draw Bode plot in Scilab and also get phase margin and gain margin. First of all, we need to write S equal to percentage of S, and our numerator num is equal to 3. Our denominator then is equal to S multiplied with 0.3 S plus 1 multiplied with 0.6 S plus 1. For the transfer function, we have since lane bracket S num and denominator. This is our transfer function shown here. We need to write the both parentheses TF to show the Bode plot. And we need to write show margins TF to show the margins, phase margin and gain margin. We have to insert this instruction to get the phase margin. To get the gain margin, we have to insert this instruction.
Now I will show the process of designing a lead compensator so that the phase margin will be at least 50 degree.
To design a lag compensator so that the phase margin would be at least 50 degree, so we need to find the frequency where phase equal to negative 125 degree. Using Scilab, our new gain crossover frequency omega c is 0.1127 Hz equal to 0.708 radian per second. Using Scilab, we get the gain is 11.63 dB at 0.1127 Hz or 0.708 radian per second. 11.63 dB equal to 20 log alpha. After that, we do the mathematical manipulation and get the alpha equal to 3.815. Now we are going to find out the z and tau to complete the phase lag network transfer function gc of s. So we found the z equal to as z equal to omega c over 10, so z equal to 0.0708 and tau equal to 14.12. After that, g of cs, as you can see, that 1 plus tau s over 1 plus alpha tau s. So after that, we substitute tau and alpha value inside of this transfer function, as the final transfer function become the numerator 1 plus 14.12 s and the denominator is 1 plus 53.92 s. To confirm our phase margin at least 50 degree, we need to write all of those codes inside of the Scilab software. So after that, we get the phase margin equal to 50.704248, that is greater than 50 degree. So now I'm going to show all of those instruction inside of the Scilab, and that can conclude that our phase margin of the system is at least 50 degree. To confirm the phase margin at least 50 degree, we need to write those code. At first, we need to start with s equal to percentage of s. After that, our numerator num equal to 3 and our denominator. So you can see that den equal to s times 0.3 s plus 1 times 0.3 0.6 s plus 1. Numerator for the lag compensator, denominator for the lag compensator, and other instruction g equal to numerator of the lag compensator over denominator of the lag compensator times numerator plus over denominator. So here is the transfer function, as you can see. To see the phase margin and gain margin, the Bode plot, you need to write the instruction show margin of transfer function. And here is the Bode plot for the phase margin and new phase margin and gain margin. To check the phase margin of the system, we need to write down this instruction. So here is it. As you can see, phase margin equal to 50.704248. Thank you for watching. Have a good day.